Download this code from codegive.com, link in the description below. OK, let's dive into the complexities of handling rejected bulk requests in data nodes, specifically focusing on situations where you're submitting a large number of operations. This is a common scenario in distributed data storage systems like Elasticsearch, Apache Cassandra, or even sharded relational databases. The reasons for rejections can vary, and the strategies for addressing them depend on the underlying technology you're using. This guide will provide general principles and concepts with code examples tailored for Elasticsearch, because it's commonly used for bulk operations, but the fundamental ideas apply more broadly. Understanding the problem, bulk request rejections. When you send a bulk request to a data node, you're essentially asking it to perform a series of operations, example indexing documents, updating records, deleting entries, in a single, batched call. This is generally much more efficient than sending individual requests because it reduces network overhead and allows the data node to optimize processing. However, if the data node is unable to handle the load imposed by the bulk request, it can reject some or all of the operations. This means the operations are not performed, and you need to handle the rejection gracefully to ensure data integrity and consistency. Common reasons for bulk request rejections *. 1. Resource constraints *. CPU overload *. The data node's CPU might be saturated due to heavy indexing, searching, or other background tasks, example garbage collection. Memory pressure *. Insufficient memory can lead to out-of-memory errors, or excessive garbage collection, making the node unable to process new requests. Disk I/O bottleneck *. Slow disk I/O can prevent the node from writing data to storage quickly enough. Network congestion *. A saturated network link can lead to timeouts and dropped connections, impacting bulk request processing. 2. Queue full *. Many data nodes use internal queues to buffer incoming requests. If these queues become full, due to slow processing or a sudden spike in traffic, the node will reject new requests to prevent cascading failures. This is a form of back pressure. 3. Incorrect data or mapping issues *. Data validation errors *. The data you're trying to index might not conform to the defined mapping for the index, example trying to insert a string into a numeric field. Mapping conflicts *. In dynamically mapped environments, different operations within the same bulk request can attempt to define conflicting mappings for the same field. Document size limits *. Most data nodes impose limits on the maximum size of individual documents to prevent resource exhaustion. If your documents exceed this limit, the indexing operations will be rejected. 4. Concurrency issues *. Optimistic locking conflicts *. If you're using optimistic locking, example with _version in Elasticsearch, updates might fail if the document has been modified by another process since you last read it. Index or mapping updates *. While an index is being updated, example settings changed, mappings added, some operations might be temporarily rejected. 5. Temporary node unavailability *. Nodes can temporarily go offline due to hardware failures, network disruptions, or planned maintenance. If a bulk request is routed to an unavailable node, the operations will be rejected. 6. Throttling or rate limiting *. Some systems implement throttling mechanisms to prevent individual clients or applications from overwhelming the cluster. If you exceed the configured rate limits, your requests might be rejected. Handling rejected bulk requests, strategies and code examples, Elasticsearch focus. The key to handling rejections is to 1. Detect rejections *. Parse the bulk response to identify failed operations. 2. Analyze the reasons * determine why the operations failed. 3. Implement retry strategies * attempt to resubmit the failed operations. 4. Implement backoff strategies * introduce delays between retries to avoid overwhelming the system. 5. Monitor and alert * track the rate of rejections and trigger alerts if it exceeds acceptable thresholds. 6. Optimize bulk size * experiment with different batch sizes to find the sweet spot. 7. Optimize indexing * indexing is CPU intensive, and can be the main culprit of rejected requests. 8. Check cluster health * monitor the Elasticsearch cluster health for any issues. Code example, Python with Elasticsearch. Key improvements and explanations. Explicit error handling * the raise _on_ error equals false flag in the bulk call is critical. This prevents the function from raising an exception on the first error, allowing you to process the entire bulk response and identify all failures. Detailed error analysis * the code now iterates through the errors list returned by bulk. It extracts the status _code, example 429 for too many requests, and the error _reason from each failed operation. This information is essential for determining why the operations failed. Retriable error identification * the code identifies retriable errors, specifically, HTTP status code 429, which indicates that the server is overloaded and the request should be retried later. You might need to add other status codes based on your specific error conditions, example 503 for service unavailable, 409 for conflict in some cases. Retry logic * the code now keeps track of the original actions and tries to find documents by _ID. Retry logic. Implemented a retry loop with a maximum number of attempts. Only operations that failed with a retriable error code, 429, are added to the retriable _operations list. Exponential backoff is applied before each retry attempt. Exponential backoff * the initial _backoff and backoff _time variables implement exponential backoff. The delay between retries increases exponentially, 1 second, 2 seconds, 4 seconds, etc., to avoid overwhelming the system. This is crucial for preventing cascading failures. Chunking * the chunk _size variable allows you to control the size of the bulk requests. Experiment with different values to find the optimal size for your environment. Smaller chunks might reduce the likelihood of rejections but could increase network overhead. Logging * comprehensive logging is included to help you debug issues and monitor the retry process. Create _index, function * a function to create the index, including optional settings and mappings. It also demonstrates checking if the index exists and deleting / recreating it if needed. Be careful with this in production. Handling exceptions during bulk indexing * added a try except block to handle exceptions that may occur during the bulk indexing process, example connection errors, timeouts. Includes retry logic with exponential backoff. Total count iteration * the data iterable is reset after the sum to avoid exhausting the generator. Important considerations and tuning * 1. Elasticsearch cluster health * before you even start optimizing your code, check the health of your Elasticsearch cluster. Use the _cluster/health API endpoint to see if any nodes are overloaded or have other issues. Address these problems first. If cluster is yellow, it needs fixing. Red, you have issues to solve immediately. 2. Elasticsearch node configuration **** thread _pool.bulk.queue_size ** the setting controls the size of the queue for bulk requests. If the queue is full, requests will be rejected with a 429 error. Increase it with caution because it consumes more memory. You can set this in elasticsearch.yml. *indices.memory.index_buffer_size*. The setting controls the amount of memory used for indexing. Increase it if you have sufficient memory. *indices.breaker.total.limit*. The setting limits the amount of memory that indexing operations can use. Make sure it's not too low. 3. Optimize indexing *. Disable refresh interval * during bulk indexing. Temporarily disable the refresh interval, index.refresh_interval, -1, to improve indexing speed. Remember to re-enable it after indexing is complete. Disable replication * if possible, temporarily disable replication, index.number_of_replicas, 0, to reduce the load on the cluster. Re-enable it after indexing. Be aware of the risk of data loss if a node fails during this time. Adjust shard allocation * temporarily disable shard allocation during bulk indexing, cluster.routing.allocation.enable, false. Re-enable it after indexing. Use auto-generated IDs * if you don't need to specify document IDs, let Elasticsearch generate them automatically. This is generally faster. For monitoring and alerting *. Use Elasticsearch's monitoring tools, example Kibana, Prometheus, to track CPU usage, memory usage, disk I/O, and queue lengths. Set up alerts to notify you if any of these metrics exceed acceptable thresholds. This will allow you to proactively address performance problems before they lead to rejections. 5. Data mapping *. Define explicit mappings for your indexes. Dynamic mapping can be convenient, but it can also lead to performance problems and unexpected behavior. Specify the data types for each field to ensure that Elasticsearch can optimize indexing. Use the keyword type for fields that you'll use for exact match filtering, and the text type for fields that you'll use for full text search. 6. Network *. Ensure that you have sufficient network bandwidth between your application and the Elasticsearch cluster. Use persistent connections, HTTP keep alive, to reduce connection overhead. Consider using a load balancer to distribute traffic across multiple Elasticsearch nodes. 7. Document size *. Keep your documents as small as possible. Large documents can consume more resources and increase the likelihood of rejections. If you have large documents, consider breaking them down into smaller, more manageable chunks. 8. Rate limiting *. If you're sending a large volume of data, consider implementing rate limiting on your application side to prevent it from overwhelming the Elasticsearch cluster. Use the _bulk APIs _source excludes parameter to reduce the amount of data that's transferred over the network if you don't need the entire source document. 9. Garbage collection *. Monitor the garbage collection, GC, activity on your Elasticsearch nodes. Excessive GC can lead to pauses and performance problems. Tune the JVM garbage collection settings to optimize performance. 10. Coordination node *. If you are sending bulk requests from a dedicated client, consider using a dedicated coordination node that does not hold data. By carefully considering these factors and implementing the strategies described above, you can significantly reduce the likelihood of bulk request rejections and ensure the efficient and reliable indexing of your data. Remember to adapt the code and the specific settings to your specific environment and requirements. Good luck.